So welcome back. So far, in talking about tuning sparse matrix vector multiply, I've only talked about one optimization. There are a lot of optimizations, and here's kind of a list. So far I've only talked about register blocking, breaking up the matrix into these little blocks, 4 by 2 or 8 by 8. And as I mentioned, you can get up to 4x speedups. That's a good thing. But it could be that your matrix doesn't have the single block size that it likes. It could be that 4 by 4 blocks work well for a part of it, and 3 by 3 blocks work well for a part of it. You'd like to split your matrix in two and have two different data structures for different parts. That can also give you a nice speed up. In fact, a factor of 1.8 on top of using just one data structure. Some matrices are stored very naturally as a bunch of dense diagonals because they come out that way. That's a different data structure. That can also give you a factor of 2 on top of the vanilla data structure, CSR. It may be that your matrix has no dense blocks in it, but if you reorder it, if you replace your matrix by permuting the rows and permuting the columns, you can get lots of dense blocks. And of course, you have to refactor the rest of your algorithm to deal with that permutation, but that can give you a large factor of speed up. If your matrix is symmetric, you can, of course, only store half of it. That gets you another factor of 2.6, more than a factor of 2 by only storing half the matrix sometimes, because you might use a different block structure if you exploit symmetry. There's blocking not just at the register level, but at the cache level for all the usual reasons. That can give you another large factor. If you're going to multiply by more than one vector at a time, which is not unusual, that can give you factors of 7. There's just lots of reuse in that case. And of course, all of these can be combined in different ways. This is not something you want to do by hand. You can also apply this to solving sparse triangular systems, not just sparse matrix vector multiply. But the real payoff comes from not just a single sparse matrix vector multiply, but by recognizing that most algorithms are doing a lot of them. The simplest thing you could imagine doing, if you're computing a singular value decomposition, what's the inner loop of your algorithm? You don't just multiply by x. You're always multiplying by a and a transpose times x. So if you think about it, you can convince yourself, all you do have to do is read your matrix A from memory once, and you can do both of these interleaved. Right? That cuts your memory traffic in half and doubles your speed. And in fact, this is the kernel that wins, doing many, many matrix vector multiplies at the same time. And I'll have more to say about that later. But let me just give you an example of how much reordering pays off. So this is a matrix I showed you earlier on. It's from accelerator cavity design. And sparse matrix vector multiply is the bottleneck. So this matrix, if I were to zoom in, and I'll do that in a moment, has no dense blocks. So let me try to reorder it to try to create dense blocks. And a very classical way to do that is to reorder the rows and reorder the columns using breadth first search. It's called reverse Cut-Hill-McKee, RCM. What that tries to do is push all the non-zeros toward the diagonal. And intuitively, if they're all crunched together near the diagonal, I ought to have a lot more dense blocks, right, that I could take advantage of. So let me look and see what happens. So I'm just going to zoom in on the top 100 by 100 corner. This is the original matrix, and there are hardly any dense blocks. Let me now do reverse Cut-Hill-McKee and see what happens. So I've color-coded it to see what happens. The green entries are the same before and after reordering. But the red ones in the original matrix got moved to the blue ones. They all got crunched toward the diagonal, and now I have lots and lots of dense blocks. This is a good idea. But there's another scheme we can use to even create more dense blocks. And the question is, in what order should I put the columns so that adjacent columns have as many non-zeros in common as possible? If you think about it, that's a classical combinatorial optimization problem called the traveling salesman problem, which, of course, is hard to solve exactly. We don't care. We're going to approximate it. And if we do that, do another very cheap phase of the traveling salesman problem, this is what we end up with. So all the original entries that were red have now moved into the blue areas, and it's all big, dense blocks. And we get big speedups. Now we can apply all of our register blocking tricks, and we get speedups of 1.7, 2.1, 3.3, depending on the platform. But if we tried any of those in the original matrix, it wouldn't have worked at all. But of course, now we've changed our matrix. It's not A anymore. It's P times A times P transpose, where P is a permutation. And so what that means is that when you use that multiplication in your algorithm, you have to remember that P is there. And depending on your algorithm, you'll have to change it appropriately. But if all you want are eigenvalues, they haven't changed at all, for example. You get the same answer. But it just depends on your problem. OK, so this is an enormous number of different optimizations. We have tried to package them all into this OSCE optimized sparse kernel interface to try to hide all these details. So it's going to attempt to do all of the optimizations I've listed for you automatically. You can just trust it and say, please tune. and it'll try them. It won't try them all because it's not smart enough to try them all yet. Or you can give it hints. You can say, I think that it's worth trying to reorder my matrix, or I think it probably has 8 by 8 blocks, if you want to give it that hint. And even more important, you can say, oh, this is the same matrix as yesterday. Just use whatever I did yesterday. And it'll go look up in a database and use that. Because typically, if you're doing a big development project, your matrix may be the same for quite a while over a sequence of runs. So its interface is very much like the BLAS, right? You pass in a pointer to your matrix, to your vector x, and it comes back with a pointer to your vector y. It's available as a standalone library, and there's a website for it. And it's also been incorporated into PETC, which is sort of a standard high-performance computing MPI environment. And this is used, if you have a big sparse matrix that's spread across your whole machine, OSCI is called processor by processor to optimize the local part of it. So, and as I said, we're trying to hire someone right now to work on putting all the multi-core optimizations into it. So it doesn't have that yet, but we have the multi-core optimizations, but it's not in here. I'll show you the multi-core in a moment. So this is sort of the architecture of the tuning system. There's an offline part, and then there's an online part. And so what do we do offline, where we try to do as much work as possible? For each target architecture, we benchmark all those different possible register block sizes I told you about, all 144 of them. And we keep a table of how fast they would run in that particular architecture. And we also generate the code so that we can very quickly just sort of grab that precompiled code at runtime. So what happens at runtime? The code is going along. The matrix becomes available. You also have a workload. I mean, your OSCI monitors your program. It says, oh, you've done a lot of matrix vector multiplies. Or you're doing not just multiplications by A, you're multiplying by A transpose. It keeps track of all that, and it monitors your workload. And you can also tell it to say its history, right? Same matrix as yesterday. And then what it does is it takes those models, of which I gave you a hint about, and it evaluates them at runtime, and it picks what it thinks is the best data structure. It reorganizes your matrix for you and hands you back a handle, sort of an object-oriented opaque handle that you can use to call matrix multiply with. So let me give you some samples of code of how it works. So let's suppose this is your vanilla code you're starting with, written in C. And I'll say how you would gradually change it to use OSCI. So you have a bunch of, so you declare your matrix. So there's the array of pointer, indice, and values. And so you've got to fill those in. So you build your CSR the way you had before. And you also have your x and y vectors. And let's suppose that here's your matrix multiply loop. You're going to do 500 matrix vector multiplies and, with your subroutine. I want to change that to do tuning. So what I have to do is put wrappers around your matrices so that OSCI can have its own copies, because it's going to manipulate those opaquely to you. So you do an OSCI, you create a new object, which is an OSCI matrix type, and you give it a name A-tunable, and you do an OSCI create matrix, and it makes a copy of all of your data. It doesn't change your initial data structure, and it keeps its own separate copy, which it's allowed to do whatever it wants with. And similarly, you got to tell it, you get an x vector and you get a y vector. So that's the first thing you got to do. But I haven't changed the matrix multiply yet, but now OSCI knows something. And then the easiest thing to do is you change my matrix multiply to OSCI matrix multiply. And you pass in, you don't pass in your matrix anymore, you pass in the OSCI version of the matrix, A-tunable. So far, still, no tuning has been done, but that's most of the work, sort of just, this very simple change. Now you can ask it to tune. And for example, you can give it hints. You can say, I'm going to call matrix vector multiply 500 times. So you can say OSCI set hint, number of times I'm going to tune it is 500. All right, there's a whole bunch of hints that you can give it. And you can also say, for example, if you happen to know that you think it has 8 by 8 blocks. Right? If you know that stuff, you can just go ahead. And then you say OSCI tune. And it will use those hints or not. It'll do whatever it thinks is best. Reorganize the matrix inside, and the next time you call matrix multiply, it'll do the right thing. Now, it may be that you don't have any hints, or you don't know anything about your matrix. Then what's the very simplest thing you could do is you could just say tune in the inner loop. Every time you call matrix multiply, you say, oh, tune it. This looks like a bad idea, right? I told you that tuning was expensive. Well, what tuning does actually, all it does is it monitors the workload. All it does is records that, oh, you just called matrix multiply, and you called it on A, not A transpose, and so on and so forth. It just records data. And maybe after 100 times, the 100th time, it'll say, I think you've done it enough, it's worth tuning now, and then it will change it and do all of that changing for you. And the next time it'll be fast. Right? So that's another way to use it. And finally, if you're an expert, you can write little scripts that tell it what tuning mechanisms to use. In Lua, a little scripting language called Lua, which is widely used, you can have a little file which is called mytransform.text, and you can say, please go use that transform that I figured out before. So what would your little transform look like? You might say, please reorder the matrix using the traveling salesman algorithm. That's one of the built-in things. We don't know how to guess that that's a good idea. You have to tell it explicitly, but it just is one line of code. And then you might say, well, I'm pretty sure I have 2 different finite element sizes in here, so please split it into blocks. Split it into 2 by 2 blocks and whatever's left over. And then when you actually want to multiply by the matrix, you got to do the permutation. You got to multiply separately by the parts with 2 by 2 blocks and 1 by 1 blocks, and then you got to do the reverse transposition. And this is your code that would say, do that. And you could also say, look in the database and just do what I did yesterday. So this is kind of the expert interface, but we're not smart enough yet, or OSCE's not smart enough yet to figure that all out for you. Now, we've had some new requests, and your input is welcome here too. These are the folks in Trilinos, which is one of these libraries like PETSI that's used in the Department of Energy. It turns out that users don't just create one matrix, they're constantly updating it during the course of the run. They'd like to change the non-zero pattern, right? Because they're in some optimization routine and they still want it to go fast. And so what they'd like to be able to do is stick in new non-zero entries, which you can't do right now because we have an opaque interface. And also, the way that matrices often get built is that you have one program that analyzes part of your finite element problem. It builds part of the matrix. Another one builds another part. And you'd like to be able to put them together easily because that's how sparse matrices get built in practice. And so their proposal is that we have a new data structure for sparse matrices, which is basically a sum of independently tuned fragments. All of these could be computed independently on different processors, whatever. Each one could be tuned separately. And when you do a matrix vector multiply, you multiply by A1, and then you multiply by A2. You do all those separately, and you add it up. But occasionally, you might say, if I've added a lot of, 1 by 1 entries, it's probably worth reorganizing it and retuning at some point. So there needs to be a merge routine, which will take some big, long thing and say, is it better to crunch it down into something smaller? And so we're hoping to have these new routines put in there. But this is sort of an interchange with users, and so it's a design that's transferring over time. Okay, so now let me talk about multi-core, because I haven't talked about that yet. And these are optimizations that are not yet in OSCE that we want to put in. But let me show you the results of the experiments on these 4 different parallel machines, which all have different properties. I have little cartoons of them. So there's a Cloverton, which is an 8-core machine. And here are the sizes of the caches and so forth and the memories. And there's an Opteron, a Sun Victoria Falls, and a Blade. So let me just sort of tell you the important properties of these machines. So all of them are cache-based except the Blade. It's local store, so you have to have explicit data movement. Cell is kind of dead now, but anyway, let me show you the experiments. They have different numbers of threads. So for the Cloverton and the Barcelona, they're 8-threaded machines. Sony has 16. The Sun has a vast number because it's chip multi-threading, and these threads are sort of generated automatically. They don't correspond to actual cores, but they can maintain 128 threads that are ready to run. 3 of them are NUMA, non-uniform memory access. Let me go, and the Cloverton is not. Let me just go back to this picture. So if this core on Barcelona wants to access this piece of memory, it takes a different path to get to it, a longer path, than it does if it accesses that piece of memory. And if you want to run as fast as possible, your algorithm has to know that these cores should operate on submatrices that are stored here, and these cores should operate on submatrices that are stored there. That's an important optimization. And they run at different speeds. So the top 2 look like they're the fastest by far. I mean, in terms of peak, 70 gigaflops. These are much slower. We'll see whether that's true in practice. And they also have very different memory bandwidth speeds. So I just record all this data so that you can see that these may have higher gigaflop rates, but they have the lowest memory bandwidths. And since this is a memory bandwidth bound problem, you might guess that these 2 will do better. So let's see what happens. So I'm going to run all of our auto-tuning stuff, so all the sequential stuff that I told you about, plus all these new multi-core optimizations on all of these different 14 or so sparse test matrices, and these are just little spy plots, so too small to see, but they come from many different walks of life, from economics and epidemiology and whatever. I'm going to show you 4 plots, one for each machine. In each plot, I have one little column for each sparse matrix, and the vertical axis is gigaflops. And each color corresponds to a different version of the algorithm. So in particular, the naive code, no sequential, just purely sequential, CSR format, no optimizations, that's the purple, right? So that's our baseline. The question is, how much faster can we go? And the first optimization to try is just try p-threads, right? Break your matrix up into as many blocks, row blocks, that can be multiplied completely independently as you have threads. So on this machine, you break it up, your matrix, into 8 block rows. Each thread gets a piece. You should get an 8-fold speed up. They have nothing to do with one another. But you can see it's a heck of a lot less than 8-fold speed up for the Xeon. A lot less than 8-fold speed up for the Barcelona. It's a little harder to tell here. It's good speed up, but it's not anywhere near 128. And this is nowhere near 16. All right, so naive optimization doesn't work. So we have some work to do cut out for us. So let me throw in now NUMA awareness. So that is this light blue color. So that's where the processor has to know that some of its DRAM is closer to one core than to another, and it should only access that part. And we also do software prefetching, because there are explicit instructions in these machines to say, please start getting the data from memory before I need it. And the question is, how far ahead should you go? Should you ask for the next 4 words that you need, the next 8 words, the next 16 words? That's a tuning parameter. And we used exhaustive search to try all possible software prefetches. And that is the green bar on top. And so by the time you added all of that, you go to the top of all the bars. They're all stacked on top of one another, and you can see what the payoff is. So far, on the cell blade, we're not doing well. We're not using all the parallel processors, the SPEs. We're just using the PPEs. Okay. And finally, we do all the sequential optimizations that I talked about before, which here is called compression. It means register blocking. I might use a different format. If I don't need to use 32-bit integers. Maybe if I'm on a small cache block, I could use 16-bit integers, save memory traffic. And that adds the orangish kind of block at the top. Okay? So finally, we get pretty good speed ups. Let me now add one more optimization, which is cache blocking. And that only matters on your matrices, it turns out, that are really short and fat. So it really only paid off on a few of them, not very many. But it helped on those. And when I finally do everything by hand, it all has to be written in low-level machine code on the SPE. This one wins. But this was not auto-tuned. This was handwritten because that machine is just sort of unusual. And so when all is said and done, what's the speed up that we get compared to doing naive p-threads? Doing it the obvious way, those are the speed ups, in the best case. So it was well worth doing. And as I said, this is not NOSCI yet, but we hope a future release will have it. Okay, so that's all I wanted to say about tuning a single sparse matrix vector multiply, which is the inner loop for many algorithms. And the next thing I want to do is go beyond that and say it's not enough to tune a single sparse matrix vector multiply. Whatever we do, it's going to be memory bound. I have to tune something at a higher level. I have to tune the entire solver that calls the sparse matrix vector multiply. Only then do I have a chance of having a high computational intensity. So let me tell you the basic, what we're going to do. So what I want to do is think about taking k steps, k sparse matrix vector multiplies of a typical sparse solver. So, and they have names like conjugate gradient, GMRes, Lanczos, Arnoldi. So I have a loop from 1 to k. What's the inner loop do? It does a sparse matrix vector multiply, and then it does some vector operations, basically, is what it looks like. So what I want to do is take that entire operation and minimize the communication. And I'm going to assume that my matrix can be kind of partitioned well. That means I can find good separators. I can give each processor a chunk of it, and there are not too many connections with other processors. So 2D meshes, 3D meshes are the canonical pictures, but it can be quite irregular. So here are the results. In the parallel case, what's the conventional algorithm do? I'm doing k sparse matrix vector multiplies. The cost is going to go proportional to k, right? Because each sparse vector multiply is going to be a reduction operation, log p processors. So the cost is going to grow proportionally to k. The new algorithm, it's not proportional to k. It's independent of the number of steps that you take. There's a single reduction operation that's enough to take k steps of the algorithm. You can't do better than that. What about the serial case? In this case, I have my sparse matrix. It lives in DRAM. Every time I do a sparse matrix vector multiply, I got to go to DRAM and bring it. And so the cost, the total memory traffic is growing proportional decay. The new algorithm, it doesn't grow proportional decay. I read it once from memory, and I can take k steps of the algorithm. So and you can't do better than that. So this is a complete reorganization of the entire algorithm. Not a single sparse matrix vector multiply, but everything. And so there's lots and lots of speedups that are possible here. But the price we're going to pay, there are going to be two interesting prices. One is that we're going to have to do redundant computation. Not very much, but flops are cheap, so I'm not worried about doing a little bit of redundant work. And also, the numerical properties are going to change. We're going to have to be very careful about how we do the transformations to get the right answer. So these are going to have different numerical stability properties than before. So let me give you a hint about how to reorganize this. And I'm going to draw it for the simplest example where I can show you everything that goes on, a 30 by 30 tridiagonal matrix on two processors, right? So we can think, you can see everything. So I have processor 1 owns the first 15 entries. Processor 2 owns the second 15 entries. And each of these little circles represents an entry of x. And each of these circles represents an entry of a times x. And since a is tridiagonal, each entry of a times x depends on 3 entries of x, right? Because tridiagonal means there are 3 non-zeros. So I've written here every possible dependency. And so if processor 1 is not allowed to communicate with processor 2 at all, what can it compute? Well, it can compute that guy. It computes ax sub 5 because it needs x4, it's got it, x5, and x6. And so all these guys can be computed, but it can't compute that guy because it would need to communicate with processor 2. So I've left out that line. So this is all I can do if I'm not allowed to do any communication. Well, what can I do next? How much of a squared can I compute? Well, same picture. I just draw all the dependencies. And everything there you see I can compute, but I can't compute that guy because he depends on him and he depends on him. All right? A cubed, same idea. There's more missing data. And finally, let's suppose I want to take 8 steps. This is all I can compute if I don't do any communication. And all of these guys are missing because they depend on something over here. Okay. So what would the conventional algorithm do, right? Because processor 1 needs to fill in everything here. It needs all this data to run the algorithm. Well, there'd be one communication to fetch that data to compute him, another communication to fetch him to compute that, and so forth. There'd be 8 messages. There'd be a total of 8 messages. I only want to do it with one message. It's pretty easy. What I'm going to do is package up all of these 8 numbers into a single message and send them as one message at once at the beginning of the algorithm. I need 8 pieces of data. I mean, mathematically, I need 8 words, right? And the answer depends on 8 independent pieces of information. The only thing I can hope to improve is what's the latency cost? And so what I'm going to do is package all these up in processor 2, send them to processor 1, and now processor 1 has enough information to fill in all of the missing data, provided it also computes all of this red stuff redundantly. So the red stuff is going to be computed twice, once by processor 2, once by processor 1. But that's okay. That's just a little bit of extra work at the boundary, right? Think of this as a really big matrix, not 30 by 30. This is a tiny little bit of stuff around the boundaries. And so now in one message, I can compute all of that at the price of computing a little bit here. And as long as I can partition my matrices nicely so there are not too many edges connecting different processors, here there's really only like one edge connecting it, then there's not much redundant work. So I package those up in one and send it as one message. So that's the tridiagonal case. It works in arbitrarily irregular matrices. So here's kind of a picture of the same idea. I mean, the data structures get more complicated. So this is a graph picture of a sparse matrix. There's one row and column for every node, and there's a non-zero for every edge. So if this is, row I and that's row j, this edge means a sub ij is non-zero. And all of these orange lines say which processor owns what. So the processor in the middle owns all of those rows and all of those rows. This processor owns those rows. So if this processor wants to compute a times x, what does it have to communicate? It has enough information to compute all of these only if it gets the stuff that it's connected to in its neighbors that's one step away, one edge away. So you follow one edge to the neighbors, you look at all the red vertices, and it's got to get those. And then it can compute an a times x. Those are called ghost zones. What if it wants to compute a squared times x? It has to go 2 edges away and get all the green ones as well. And what if it wanted to compute a cubed times x? It would have to go 3 edges out and get the blue ones as well. So what each processor is going to do, it's going to package up the red, the green, and the blue, everything within 3 edges of its neighbor, and send it off to this guy. So one message with every neighbor, and now this one in the middle has enough to compute a x, a squared x, and a cubed x. Now, that's the parallel optimization. What about the sequential case? I was claiming that I only have to read my tridiagonal matrix once from memory to compute all of these. So here's the idea. Imagine that I have a very wide tridiagonal matrix, and I'm only showing you, a little bit in the middle. And so I'm breaking it up into pieces. And suppose that I've finished computing all of the entries of ax, a squared x, a cubed x, and a to the fourth x for the first part of the matrix. Now I want to compute all of this. What do? I read in the rows of the matrix corresponding to these entries, 6 through 24. I remember these 4 entries of x, ax, a squared x, and a cubed x. I leave them in cache. And now I have enough information to compute everything in this parallelogram with no more memory traffic. So in one step, I just read the matrix in once, I leave that in, and I compute all of those entries of my matrix vector multiplies, and I've read the matrix from memory once. Okay? So there is no redundant work, and there's minimal memory traffic. So this is, so there's no redundant work here. So if I go back to this picture, I can use the same trick. What I'm going to do is I'm going to do all of the work for this guy, a squared, a cubed. Then I'm going to do that guy, and then I'm going to do that guy. So I'm going to process all these partitions in some order. The question is, what's the right order? Right? In a tridiagonal matrix, it's obvious I go from left to right or something. Right? But if I have a general sparse matrix, how do I choose the order in which to process the partitions to minimize memory traffic? Well, it turns out this is one of those tuning parameters. What's the right order? And the answer, turns out, you can formulate it again as another traveling salesman problem, which you can solve approximately to find the right order to visit all these guys. Okay, so those are, I told you about optimizations for parallelism to minimize the number of messages, and about sequential to minimize memory traffic. Well, what about multi-core, right? I got both things going on. I have information moving between cores, and I have on-chip, off-chip memory traffic. I have to use both of those optimizations I just told you about. I'm going to have to do a hybrid. I'm going to do one to minimize off-chip memory traffic, and the other one to minimize inter-core traffic. And so, let's see what happens. And so I'm going to show you some speed-up numbers. And my baseline is going to be that optimized single sparse matrix vector multiply I told you about before. So we'll use all our tricks to make it go as fast as possible for a single one on multi-core. And all of these speed-ups are going to be on top of that. And so here are the numbers on a Cloverton for doing that. And you can see they depend rather dramatically on what the structure of your matrix is. Each of these are different sparse matrices from different walks of life. And the speed-up is shown, so the vertical axis is speed. And so the red is the single totally optimized sparse matrix vector multiply. The green is how much faster we go. And the speed up is shown here, and also the value of k. How many steps do I take in order to make it go as fast as possible? So this was an Intel Cloverton. But we're not done yet, because what is this good for, right? I mean, what can I use ax and a squared x and a cubed x for? None of the solvers that people typically use this algorithm, right? I have to reorganize the whole solver now to take advantage of this. So let me tell you on one slide how to take just one solver and reorganize it so that instead of doing sparse matrix vector multiply, it uses the kernel I just showed you. And so this is a very high level kind of cartoon of that algorithm. It's called GMRes. I'm going to take k steps. I do a sparse matrix vector multiply. Then I do something called modified Gram-Schmidt to make the vector I just computed orthogonal to all the previous vectors. It's lots of dot products and Saxbys. And then I do some little stuff that's on little dense matrices. It doesn't cost very much. And I do that k times. And so what is the cost of this? It's k sparse matrix vector multiplies k squared vector operations. And the cost is growing proportional to k. So I want to change that so it can use the kernel I just showed you. So here's what it is. I have a single call to this kernel that computes in one communication, ax, a squared x, or v, so forth. And I get a whole bunch of vectors. I get v vectors. What am I going to do to those vectors? I need to compute a QR decomposition. I'm going to use that tall, skinny QR I told you about in the dense case. My communication avoiding tall, skinny QR. And that minimizes the communication in the dense part. And now my communication cost has gone down by a factor of k. So this seems like it does everything I could want, minimizes communication. But there's one bug. Let's make sure we get the right answer, right? I mean, everything I've told you is completely true in exact arithmetic, but we're not doing exact arithmetic. We're doing floating point arithmetic. So let's just run an experiment and see if it converges. Okay? And so the horizontal axis is the number of steps that I take. And by the way, k is 24 here. So I'm doing a chunk of 24 vectors at a time. The vertical axis is the log of the residual, which I hope goes to 0. The classical algorithm is this black line here, and it's converging. And here's the algorithm that I just told you minimize communication. And it's not converging at all. And there's a reason for that. If you look at these, all of these vectors are actually getting more and more nearly parallel. They're getting nearly parallel to the dominant eigenvector. And in fact, this is the PageRank algorithm. This is how Google computes the dominant eigenvector of the PageRank matrix just by repeatedly doing matrix vector multiply. And so if these vectors are nearly parallel, they're losing information. It's numerically unstable. So I have to fix it. And the answer is very simple. Instead of computing ax, a squared x, a cubed x, I can choose different polynomials. I mean, a squared, a cubed, those are particular polynomials. I'm going to choose a different set of polynomials. And I'm going to choose them so these vectors stay numerically independent. And there are well-known ways to do that. And so it changes the algebra. I got to refactor the algorithm, but it all works now. And now I get this green line, and it works. Okay? So the point here is that it's not just the computer science you have to get right. You have to get the numerical analysis right, too, and then you can sort of put the two together, and you get your speedups. Okay, and when you finally do it all, let me show you the speedups in Cloverton for the entire solver. This was papered supercomputing. So lots of different matrices. And it's normalized, and it's comparing the runtime of the new algorithm, which is always normalized to 1, to the runtime of the old algorithm. And it's broken down into the pieces so you can see how much of the speedup's due to getting the sparse stuff right and how much of it's due to getting the dense stuff right. So let's just look at this one. So here, the standard sparse matrix vector multiply is blue, and that shrank to red. So the blue shrank to the red. So that's part of the speed up from getting the sparse stuff right. And the modified Graham-Schmidt, the dense linear algebra, that's the purple, and that shrank to the orange plus the yellow. So part of the speed up is due to getting the dense right, and part of it is doing the sparse right. And for each matrix, it's a slightly different story, but both were necessary. Okay, and there's similar data on Nehalem. Nehalem, the speedups aren't quite as good. Why? Because Nehalem has more memory bandwidth than Cloverton did. So avoiding communication isn't quite as important because it has higher bandwidth, but it's still a good idea. Okay, so let me just give a 2-slide summary of what's known. I sort of gave you a tour of just one algorithm, GMRes, and we know how to do that. And one thing that turned out to be harder to do the auto-tuning than it was before. So the way we first did this is we said, okay, let me take my kernel, a squared, a cubed, tune that as well as I can. Then let me take my tall, skinny QR, tune that as well as I can, put them together. That's the first thing we did. And it was terrible. It slowed down. Why was that? The two kernels were fighting one another over the cache. They were individually tuned, but when you ran one after the other, it was bad. What we had to do was go back and co-tune them. We had to make sure that they were compatible with one another in the tuning process, and then we got all those speedups. That's something we call co-tuning. Something we did by hand to get those speedups. Something that we have to automate in a way to be determined, right? So the tuning spaces have to be coupled. We know how to do this stuff for other Krylov subspace methods, like for Arnoldi and Lanczos, which solve eigenvalue problems for conjugate gradients. But there are a bunch of other ones that are still to be done, ongoing research, because there's an awful lot of. Remember my decision tree. There are a lot of these methods. Haven't done them all yet. There's also something called preconditioning, which people often use to solve these problems. And so what does that mean? Instead of solving AX equal B, maybe A is a very hard, difficult matrix, I'm going to replace it by MAX equals MB, where M is an approximate inverse. It's sort of approximately A inverse, but it's very cheap to multiply by it, so hopefully this will converge faster. And so a typical example, well, there are a lot of examples of different M's. So you can redo all that algebra, and your kernel is not a squared, a cubed anymore. It's this funny alternating product of A's and M's and A's and M's. That's what we need to do to get it to work. Now, then we have to ask, is there any hope of minimizing communication for this rather more complicated kernel? If M is diagonal, it's trivial. You can do that. If M is sparse, it can still be done, maybe. But most preconditioners are actually not sparse. They're dense. But they're very cheap. For example, M might be solve a tridiagonal system of equations. So M is explicitly the inverse of a tridiagonal. It's dense, but you do it by solving a tridiagonal, which costs order n. It's very cheap. But it turns out we can do it for a large class of these. This is sort of a mathematical digression. They're called hierarchically semi-separable matrices. And for those, it is possible to do this. But there's a lot of ongoing research. And let me just say there's a recent PhD thesis which began to scratch the surface of this. Okay, so let me end the sparse matrix stuff by saying, what is a sparse matrix? I mean, right now, we've been talking about standard sparse matrices where it's stored in CSR format, but that's actually just one piece of a little design space. What do I mean? That means that we are storing the values, the non-zero entries. They're stored explicitly, a list of values. And we're also storing where their entries or indices. That's explicitly stored. But that's not the only way you can store a sparse matrix. There are a lot of other ones. So for example, in one of the Parlab applications, content-based image recognition, which you'll hear about shortly, in that case, it was also a sparse matrix, but we didn't have to store the indices. It was very, very structured. Basically, you had an image, and there was one row and one column for every pixel, and the ijth entry was how much pixel I was similar to pixel j. And so we didn't have to store all the indices, and we also only stored the non-zeros if pixel I and pixel j were close enough together, within 20 pixels of one another. So that's what made it sparse. But we don't have to store the indices. We just know that it comes from an image, and all the loops are arranged correspondingly. So that says that the structure is implicit. Another example is stencils. That means like maybe all your data lives on a 2D mesh, and your matrix says, please average with your north, south, east, and west neighbors. Just compute the same average at every point. That's also a sparse matrix, but now I don't have to store the indices, and I don't even have to store the non-zero entries because they're the same everywhere. People do that a lot, and I have a few minutes to talk about tuning that. So the point is, the notion of a sparse matrix, is much larger, and the hope is that we can reuse a lot of these ideas for all these other classes of things that are really sparse matrices in disguise. So just to conclude then, so minimize communication. I think I've said that enough times now. We can generate fast code for a single sparse matrix vector multiply. That's worth doing. There's a big design space. It has to be searched at runtime, so we need lots of heuristics to make that happen. But the biggest speed-ups come from taking the entire sparse solver, the entire GM-res algorithm, and reorganizing it in a non-obvious way so that the entire thing minimizes communication. And we have lots of papers on this ongoing research, and there's a website for it. Okay. So that's the end, I think, now of sparse. And this is a good time to stop for questions. I just have a few slides on stencils, and then I'll quit, since I think time is flying. So any questions about this before I go on to structured grids, which is to say stencils? So this is a case where all your data lives on, let's say, a 2D mesh or a 3D mesh or whatever. And at each mesh point, you're going to compute the same function of the mesh point and its nearest neighbors, right? So you might take, the average of its neighbors with the mesh point and replace it. So that means that the coefficients are all the same, the function you evaluate at every point is the same, and the indexing is simple. So what are the opportunities for tuning? And so this is work that Sam Williams has done. So let me give you some examples, just to give you a hint. So the simplest kind of mesh that you could imagine, in this case, is a 7-point stencil. It's a 3D grid. It comes up often when you solve PDEs. So I have all the grid points are indexed by 3 indices x, y, z. And at every grid point, I'm going to take my 7 nearest neighbors in my north, south, east, west, in and out directions and compute the same function at every point. And so this eliminates some tuning opportunities we had before. I mean, there's no memory traffic for the indices because we know them all implicitly. There's no memory traffic for the entries of the matrix because we know all of those implicitly. But there's still a lot of things to do. And all of these are color-coded by all the different tuning opportunities along the bottom. So all of these different colors represent the different tunings that were done in order to get to the very top, which is the ultimate speed-up. So this is a 7-point stencil on, I think it was a 64-cube grid, on an Opteron, a Cloverton, and a Victoria Falls, on a different number of cores each. So you would hopefully get linear speed-up. And it's taking the naive code. It's adding the NUMA and affinity optimizations that I told you about. You want each core to only access the memory to which it's most closely attached physically. You want to add zeros into the array. You want to pad it out to make sure that things are aligned on those boundaries so that you don't overrun. You want to do register blocking for all the same reasons as you did in sparse matrix vector multiply. You want to use software prefetching. Cache bypass, there are different instructions. If you know something is not going to be reused in cache, you might as well send it directly to memory. And there are special instructions that can do that. And finally, you can apply these in all sorts of different orders. And so you can try searching several times through all different possible orders. And you can see that all of these are necessary in order to get all the speed up. There's the naive code. And in fact, 8 cores ran slower than 4 cores on an Opteron if you just ran the naive code, even though it looks like an embarrassingly parallel problem. And only if you did everything did you get your linear speed up. And there's a similar, it isn't quite as dramatic on a Cloverton, but it's still there. And it's similarly dramatic on a Victoria Falls. This is the simplest possible stencil. Let's take a much more complicated one, which is from the Lattice Boltzmann equation, which is an application in simulating plasma physics. It has all of Maxwell's equations for the magnetic field, and it also has fluid dynamic equations because plasma is a fluid. It's a much more complicated stencil that's going on, but it's still a stencil. But now, at every point, there are 27 data items for the velocity of the fluid. There's 15 data elements for the magnetic information. And there's 1,300 floating point operations in order to update every memory location. Right? This is a much more complicated kind of thing. And here is sort of the stencil. Everybody depends on a very large number of neighboring points. Not something you want to do by hand. Again, you want to automate this process. And let me just show you sort of, again, the results on the same 3 platforms for a 64 cube grid and a 128 cube grid. And for all the different colors refer to different optimizations that were automatically applied. And again, only by doing all of them do you get anything near a linear speed up. So the question is, how would you structure an autotuner for this? Right? This is not a library interface. Right? The difference between a 7-point stencil and the Lattice Boltzmann equations, right? I mean, it's not something you capture in a library interface. So what we're planning to do here is to let the user write the serial code that would be executed at each vertex. So the input is just your regular serial code. Then we would have kind of a special purpose compiler that would take that and automatically reorganize it to do all this. Right? This is going to require code transformations at a higher level than the previous ones. And this is a PhD dissertation topic now as we speak. And so let me actually stop there and just say that there's a lot of more work going on. People are tuning particle methods. That whole other motif has been going on. You can look at these slides on your own. So particle and cell has been tuned, fast multipole method. The tuning spaces get ever more interesting, but every one of those motifs people are actively working on because they're important. And so let me just go to the end and say summary. The design spaces for all of these algorithms and their implementations are very large and they're growing. Finding the best algorithm and its implementation by hand is getting to be a hard thing to do. And so ideally, what I'd like to figure out how to do is to kind of have a database which has mathematical ideas in it and computer science ideas. And over time, everybody writes a new paper. I mean, this works for the FFT. Every time somebody writes a new paper, they take that idea and they put it in their database, and that becomes part of their search space the next time they try to generate a faster FFT. How do we do that for all these other ones? There's not nearly as much structure as there is in FFTs, but that's what we'd like to do. So I'll stop there. So, any questions? All the slides are online already. Do we have a break? By the way, do we have a break now? I forget what the schedule is.
Yes, we have.
Okay, fine. So there's no hurries here.
Jim, was there a particular parallel framework that was used to do the parallelism? Was that just POSIX or OpenMP, and did that make any difference? They've tried.
So let me back up here. For this one, it was it was all done with pthreads. I didn't do this slide, but this was a hybrid of MPI because this application used many processors on Franklin. And the question was, how many MPI processes should you have and how many pthreads? I mean, you could have one MPI process per core, or you could have multiple cores per MPI process. That was a tuning parameter. And this slide, which I skipped, explored that tuning space. And it turned out the best thing to do was to have 2 threads per MPI process. So that was one example. And in the particle methods, which I didn't talk about, I think they explored OpenMP and MPI and pthreads all differently. Not yet TBB, but I mean that could be thrown into the mix as well. So because yeah, they do all have different properties. Let me just see if there are any other. Yeah, so that's the brief summary. I think since Sam did the work on exactly what the design space was for particle methods, I'm going to have to defer some of the questions to him. So, any other questions? So, I guess we have a break for half. Oh, great.
I have a question about software prefetching. So is this something very easy to do, and what do you do with software prefetching?
I think these are intrinsics that that depend on the compiler, and so they had a different. These are pragmas that are inserted in the compiler, and so you have to say, please prefetch data starting at this location and prefetch it this many instructions ahead, and then the compiler recognizes that and generates special assembly language instructions, and so it is compiler specific.
Okay, so it's easy to add to the existing code.
Yeah. I mean, what's easy? The question is, do you want to try all the possibilities? Maybe not. But yeah, in principle, it's easy. If you know what you want to do, it's easy to add. Yes.
Okay, thank you.
Okay. So see you all in half an hour.